So good evening students. So can you all see me and can you all hear the things? So please do type in the chat box. Can you all see the screen clearly and can you hear me? Yes? Yeah, good evening. So please do type in the chat box. Yes, so please do type in the chat box. Can you all hear me and can you all see the screen clearly? Yes? Okay, fine. So we will continue. Look here. So yesterday we have finished the first two modules of this course, fluid mechanics, correct? So basically in the first module we have seen fluid and its properties. So basically we have seen what is fluids and how we will differentiate solids and fluids, and then we have moved on to some important properties of liquids, correct? Basically fluids, correct? Even gases we have seen how's the viscosity variation and all these things. Then we moved on to fluid statics, where we have seen what is Pascal's law and then what is hydrostatic law. So from basically hydrostatic law we got what's the relation between this pressure and this depth, or basically this altitude, correct? So how pressure varies with altitude in different media. This is what we came to the conclusion, and then we have seen what's the concept of gauge pressures, vacuum pressures and all, and then we moved on to the concept of manometers, correct? So in case of manometers we have seen what are different constructions and why there is a necessity of all these constructions, correct? We have seen each and every point in pin to pin detail. Some noise is coming in the audio. Is it happening to everyone? So please do respond. Some noise is coming in the audio. My mic is in a correct position. Okay, fine. Okay, so I think once it's an internal issue for you. Look here. So basically we have seen what are the different types of manometers. Basically U-tube manometers, then after inclined tube manometers, and then U-tube manometers, inverted U-tube manometers and all, correct? So we have seen all these things. So from today we are going to start a third module of this course, which is hydrostatic forces on plane surfaces and of course curved surfaces. So basically the idea is to study about hydrostatic forces. Means if a fluid is at rest in a static condition, then what is the force exerted by this fluid on a submerged or partially submerged body generally, correct? This is what we have seen, and of course we deal with only surfaces. We don't deal with bodies in general, we deal only with surfaces. So basically this module carries out for two sessions. This is first session on plane surfaces, hydrostatic forces on plane surfaces, and in tomorrow's class we will deal with hydrostatic forces on curved surfaces. So basically these two sessions could be sufficiently good to have some idea on hydrostatic forces in a fluid. Okay, sir, there is tick 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 sound coming. What was that tick 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 sound? Good. Is it happening to all? So please do type in the chat box. Is that tick 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 sound coming to all, like how Rajnish is getting it? Is it coming to every one of you? So please type in the chat box. Yes, acha, it's coming to all of you. But I think the settings are as usual. Maybe from mic. This mic is also in a leveraging position. Okay, noise is there. Fine. Okay, we'll continue till the moment that noise dominates us, but till then we'll have the session. Okay, fine. Okay, so chalo, let us start our topic. So basically this hydrostatic forces on plane surfaces. Hydrostatic forces on plane surfaces. Now let us see how do you measure or how do you find this hydrostatic forces, and in general what are the forces that are exerted by a fluid which is in static condition on any surface. Let us try to see this. So for that let us take an inclined tube, a fluid, a bulk of fluid. So let us suppose there is some bulk of fluid. Look, this is some important thing that we need to study about. As far as gate is concerned, some questions are being asked in this, and also in practical applications this is very useful for us. Okay, so see, here, let us suppose this is some expanse of static fluid. Okay, so if this is some expanse of static fluid, now let us suppose there is some plate in this. Let us suppose there is some plate in this. Okay, let us suppose there is some plate in this which is inclined at some angle to this. Okay, so let us suppose there is some plate which is inclined at some angle, and let us suppose this angle of inclination which we are having here is, let us suppose if this is the case, then this angle of inclination with this free surface, this angle, let us suppose it's making an angle let us suppose this is making an angle theta. So this angle is theta, for example. Okay. So now let us try to project this. If you try to project this, see carefully. Let us suppose if I am projecting to show you how does the area of this look like. Okay, fine. If you project this, look, let us suppose if you project this, then let us suppose this is the area of your projection. So let us suppose this is having some area like this. So basically if you see it from the top view, then this is the area which you can get here. Result, sir, XC में paper cut guy, sorry, क्या हुआ? Anything, fine. So see here, let us finish this topic. Then after, in the last, you can ask all your queries. Definitely, we will, address them. So let us suppose if this is some plate which is or plane surface which is inclined at some angle theta to this free surface of this liquid. Okay. So then after, if this is the top view, means if this is the area of this plane, actually look, if my palm is the plane, this is the view which you are seeing. So in this view, definitely you will be seeing some straight line. But if I see from this point of view, then definitely I can get some area here. Correct. So let us see what is the total force which is acting on this plate by this fluid. Normally, if you see both the sides are fluid, then the net effect of force on this plate is 0. Correct. Let us suppose if there is both sides fluid to this plate, then definitely if you take one point, the pressure at this point will be same as the pressure at this point almost, and these two will be opposite and collinear in action, so they cancel out. So now see carefully. Let us suppose if one end is free to atmosphere and one end is filled with this liquid, okay, which means let us suppose if I am talking about gauge pressures at this particular point. So see carefully. Let us suppose if I am talking about some pressure at this point. Okay, so let us suppose the pressure at this point is P. Now this point corresponds to look, this point corresponds to some area here. Correct. This point definitely corresponds to some area, and let us suppose the area which you are taking here is some small area which is dA. And now let us set a reference axis. If this is your horizon, let us suppose this is your x-axis, and let us suppose this is your y-axis maybe. Okay, so let us suppose this is your y-axis along this. Okay, so let us suppose this is your y-axis as well. Okay, so this is your x-axis and this is your y-axis, and this plate is at some inclination to this free surface. Okay, so now if you see what is the small force that is acting on this elemental area because of this pressure at this location. Let us suppose this location is at a distance of, y. Look here. Let us suppose this location is at a distance of y from this plane. Okay, so see, let us suppose this distance is y. Okay, and this angle is theta, or else let us write this y a bit carefully, y. So now if you consider the effect of this small force on this elemental area dA, can I write the small elemental force that's acting on this elemental area dF is equal to P times of dA, because force acting is nothing but pressure into area on which this pressure is acting. So can I write dF is equal to P times of dA? So please do type in the chat box. Can you all understand that if I say the small force because of this pressure on this elemental area dA is P into dA? Yes or no? Please do type in the chat box. Can I tell this? The small force which is acting on this elemental area is P into dA, where P is the pressure at this instant, and pressure is always normal and compressive force. So definitely I can plot this pressure which is perpendicular to the line of action of this plate. So can I write this? If I can write this, look, if I want the total force, then what can I do? I need to integrate this complete expression on this PdA. Correct? Or the complete area, I need to integrate this expression. Now, before going to this case, look carefully. Let me try to tell you something. In mechanics, you might be probably knowing this. See here, if this is your horizon, if this is your x, and if this is your y-axis, for example, and if you have some area A, this area is of some magnitude which is A. Now, if you take a small elemental area here which is dA, whose this distance is y, for example. Let us suppose if this distance you are talking, then this distance is y, let us suppose. Then if I write integral over A, complete area y dA, what will be this equal to? Look, from your strength of materials or from your centroids formula, you might be knowing your y bar is equal to actually, I am sorry, this is x. Look here, this should be x, correct? So, this is x because it is measured from y axis. So, this definition, I mean this distance has to be x. So, if this is x, integral over A x dA. From your basic knowledge of centroids, can you tell me that this x bar is equal to integral over A x times of dA divided by the integral over A dA? Can you remember this formula? Yes or no? Can you recall this formula from your basics of centroids? If this is x bar is equal to double integral of A x times of dA, then see carefully. Then what do you have? This x bar is equal to integral over A x into dA divided by area of the region, which is this capital A, correct? So, which means can I write this double integral of area A x times of dA is equal to area of this region into the distance of centroid from y axis? Can I write this? Let us suppose if this is the centroid of this complete plane figure, which is x bar at a distance of x bar from y axis, then can I write double integral of A x dA is equal to area into x bar? Sir, I still having noise, sir. I think technical issue in your mic. Okay, but here it's looking, you know, pretty much cool. Anyhow, Vamsi, we'll try to see. But let's now. I think the noise is not much, correct? Because people are fine. So let us continue the class. If at some point if noise dominates my voice, then you can definitely, we'll stop the session. Clear? Fine. So see here. So this is what we have. Integral of x dA is equal to area into x bar, correct? This is what you know. So if you go here, look, dF is equal to P times of dA, correct? D times P times of dA. Now, see carefully. This implies F is equal to double integral over A. Look, whenever one side is open to atmosphere, here the pressure which we are writing is gauge pressure in general. So, if you are writing the gauge pressure in general, so this P is nothing but rho g into, look, if this is y, look carefully, if this is y which is at a distance y, let us suppose this distance I am calling it as h for the time being, okay. So, this distance I am calling it as h. So, look here, this distance which is coming here, let us suppose if I am calling this as h, means some vertical height. Look, this distance is y and this distance is h and this is theta. So, can I write this pressure at this location which is at a vertical height of h is rho g into, look, rho g into h into dA. Can I write this? Can I write this rho g h into dA, because this point is at a vertical distance of h from this free surface, and this P which I am writing here is gauge pressure, because I am assuming that one side of this plate is open to atmosphere. So, can I write this rho g h into dA? So, for the time being, let us write this h as, this h is same as y times of sin theta, correct. So, this implies your total force acting on the plate is equal to, generally we deal with incompressible fluids, so we can take this density out as a constant. So, density into this g is a constant, so rho g into, once this plate inclination is fixed, sin theta is a constant, so sin theta will take it out into, we have integral over the region A y times of dA, correct. This is what we have. So, when we are having Pushkar, right now we do not have any idea, because this year XC aspirants was almost 10 times of last year, okay. So, let us wait for the result, and I think hopefully result may come tomorrow, okay. So, that is the issue. Look here. So, now what about this term, double integral of A y dA? This, if you compare with this expression, double integral of x dA over this complete area is nothing but area into x bar. So, now can I write this F is equal to rho g sin theta into A into y bar, and what about y bar? look, this A is the complete area of this figure. So, this A is area of the lamina, and now let us suppose the centroid is somewhere here. Let us suppose the centroid is somewhere here, CG, center of, or let us suppose centroid C for example. Okay, this is centroid, C stands for centroid of this plane lamina. Now, see carefully, if this is the case, let us suppose the distance or the length of I am sorry, let us take a dotted line. So, see here, if you take this as your region, then can I call this part which is here, can I call this total length here which is still here as, can I call this total length here as y bar? Yes or no, because this is centroid, correct? So, see here, let us suppose if you are calling this as y bar, if this is y bar, then definitely, if this is y bar, then definitely, you know, you can extend maybe till this point and you can expand this. So, this will be your h bar undoubtedly, correct? So, this will be your h bar now from this free surface, which is the height at which this centroid is located, correct? So, this will be your h bar, which means the depth at which this centroid is located in this figure. Now, see carefully. So, if this is the case, I can write this as F is equal to rho g a into, look, y bar into sin theta is there here, correct? So, what is this y bar into sin theta? This triangle is, I mean, if you see these values, this is h bar and this value is y bar. So, this is theta. Can I write this a times of y bar as h bar divided by or a h bar, because sin theta into y bar is nothing but h bar, this distance. So, which means the total force that is acting on this plane lamina is rho g a h bar. Fine. This is rho g a h bar. Okay. So, which means the total force that is acting, total force acting on the plane surface, total force acting on the plane surface is equal to rho g a, and of course, all these things are constant, and this h bar depends upon the inclination at which you are inclining this surface, correct? So, rho g a h bar is the total force, where h bar is the, where h bar is the depth of centroid from free surface, depth of this centroid from free surface, from free surface. Okay, fine. So, this is from the free surface, and of course, this h bar value changes depending upon your inclination theta, correct? Because look, initially this is my plate. Now, if I change this plate orientation, then this h bar will get, you know, this point is basically the point which is containing its centroid. So, let us suppose if this is containing C, then if I tilt this plate, means if I change this angle theta, then the orientation of this plate changes and this h bar may move a bit up or down depending upon your turning. Can you all understand this point? Can you all understand that the total force exerted by this fluid on this plate is equal to rho g a times of h bar because of this particular thing? Can you all understand this? Can you all understand that this F is equal to rho g times a into h bar? Yes or no? Can you all understand this? If you can understand till this part, then we will go for the next part. Clear? Are you all clear to this point? Are you all clear with this diagram? It is very clear diagram. Okay. So, there is nothing difficult in this. So, this is what we have. So, rho g a times of h bar. Now, one thing, how would the pressure distribution look like? Look, see here. Obviously, you had some, look, see, you have some bulk of fluid anyhow. So, see here carefully. Let us suppose you have some bulk of fluid anyhow. Now, in this bulk of fluid, if you have this plate which is oriented at some angle, of course. So, let us suppose this plate is oriented at some angle and this is the plate. Okay. So, now, okay, let us suppose this is the plate. Now, if you talk about this pressure variation, how will the pressure variation look like? See here. Pressure varies something like this, correct? Initially, there will be some pressure which is acting on this, and there will be also this pressure which is acting on this, but definitely the value of pressure at this location, which is a much bottom level than this will be higher, because in a bulk expanse of static fluid, as you keep on moving down, your pressure increases linearly. This is what we have seen, correct? So if your pressure is increasing linearly, then definitely if you compare the values of pressure at this point, if you compare the values of pressure at this point and this point, definitely this P2 will be more, means if you call this as 2 and if this is state 1, then definitely these two will be more, and you know these 2 points are connected linearly. So you can take the help of a straight line to connect these 2 points, correct? So this is how the pressure varies. Now within this we can also write the pressure variation, which I will show you now. See here. See, this is how pressure varies. Okay, so this is how your pressure varies. Fine, and you can see this is the location of your centroid. This is the location of your centroid. Look, this is the location of your centroid, let us suppose, and your this is a system of parallel forces, correct? So whenever there is a system of parallel forces, you can reduce this complete system of parallel forces to a single point, correct? Look here. You know, we can replace this complete system with a single force. So see here, let us suppose this is the force which I want to replace. Then I can replace this complete system of forces with a single force, correct? And this distance from this centroid to this free surface, which we are writing here, this distance from the centroid to the free surface, basically this distance, you know, this distance is given as h bar, okay? So this distance is given as h bar. So are you all clear till here? Yes or no? So please do type in the chat box, are you all clear till here? This F is the total force that's acting on this plate, and this F is equal to rho g A times h bar, where A is the area of this plate. So can you all understand this complete pressure which is acting on this plate can be, I mean this complete pressure force which is acting on this plate in this particular format can be replaced with a single force at, I mean with the magnitude of rho g A times of h bar because of this particular analysis. Did you all get the idea? Yes or no? So please do respond. Did you all get the idea of replacing this complete force with a single force which is equal to the net effect of all these pressure forces? Is that clear? Now one thing is very clear. The magnitude of the force which is acting on the plate is clear to us. Now let us try to see what is the, you know, location at which this point, at which this pressure acts. Look here. Let us suppose if the block, I mean if the plate is in equilibrium under this condition, or if you see for example if this plate is acted upon by this pressure force. Now see carefully, this is a pressure force. Now this plate is in static condition, of course, in this situation. So let us suppose this is the inclination theta which you are talking about. This is the inclination theta that you are talking about, correct? So now see carefully, this complete system can be replaced by a single force, that's okay, but can I keep the force at this point? Can I, instead of putting this force at this point, can I replace this force at this point at the initial edge of the plate? So please tell me, instead of having this complete force system replaced by this single force, instead of this location, can I keep this force at this location like this? So please do type in the chat box. Can you all understand? Can you replace this force at this position like this? No, we can't replace, correct? Because there is something called the static equilibrium and moments has to be balanced. Means the net moment of this force on this plate should be equal to the moment exerted by this force on this plate, correct? So definitely that can't happen, but before going for that, I would like to give you one more theory point, look, which could help you a bit. See carefully. Let us suppose you have two axes, something like this, okay? This is x, this is 0 and this is y. Now, you know first moment of area is nothing but centroid, that gives you the concept of centroid. So again this is area A. Then let us suppose again you are considering small elemental area here, okay? Let us suppose there is some small elemental area here at this case. So now if this distance is x, then if I write double integral of x square dA, means basically this integration is evaluated on this complete area. We know first moment of area gives you concept of centroid. So we have seen here first moment of area integral x dA will give you the concept of centroid. So similarly, if I go for x square, can you tell me what does this value equal to, or what is this value equal to here? Can you tell me what is this value equal to? Double integral of a x square dA. About this means you are taking the moment of this area. So that's called moment of inertia, correct? So moment of inertia of area A about OY, because basically this OY is nothing but this y axis. So basically if you write double integral of x square dA, yes, moment of inertia. So basically double integral of x square dA is nothing but moment of inertia of this area A about OY, correct? Now there is something called parallel axis theorem. If you could remember from your basic mechanics classes, then there is something called the parallel axis theorem. And what does this parallel axis theorem tells us? Parallel axis theorem, I think it should be AX. Okay. So parallel axis theorem. So what does this parallel axis theorem tells us? Look, let us suppose if you are having a coordinate system, then if this is x, this is y, and if this is 0, and if you have some area of some finite space, area A. Now if this is your centroid, centroid C, then if you have an axis which is passing through this centroid, okay, let me use a dotted line. So let me use a dotted line for this analysis. So see here, if you take an axis which is parallel to this, and of course which is also parallel to this OY. Now if you have this moment of inertia about IOY, look, if you have this moment of inertia about IOY, this will be equal to I about this axis. Let us suppose if you call this as y dash, for example, this axis if you are calling y dash, then this gives you the moment of inertia about the parallel axis passing to the centroid plus area into the distance between these two axes. Let us suppose this is the distance between these two axes, for example, x bar, for example x bar. Let us suppose in this case this is nothing but the centroid area. So this is centroid and this is y axis. So in this case it's nothing but the x coordinate of the centroid. So a into x bar square, correct? You know this. This is called parallel axis theorem. Can you all recollect this from your basic mechanics classes? Yes or no? So please do type. Can you all recollect this from your mechanics classes, that if this is OY, then the moment of inertia about this axis is equal to moment of inertia of a parallel axis which is passing to the centroid plus area times of the square of the distance between these two axes, correct? You know this. Can you all recollect this? Can you all recollect this from your basic mechanics classes? If you can recollect all these things, then we will go for the further procedure. So please tell me, can you all recollect this? Yes? Very good. So now see here, if you can recollect this, that means this complete force can be replaced at some point at which these moments are balanced for every point on this region. For that, let us consider again the same thing. Look, let us consider the same thing. So let us consider the same thing again one more time. So see here, let us try to fine. Okay, let us suppose if this is the case. Now again let us suppose this is your axis and this is the axis which is perpendicular to this. Okay, you know this, correct? So let us suppose this is your x axis and previous casely as we have taken, this is a y axis. Okay, so let me extend this a bit. Fine. Okay, so this is your y axis. Fine. And this is your horizon, and anyhow you know this angle in between the things is theta. So let us try to recollect the things. This angle is theta. So see carefully, this is theta. Now again if you project it a bit, project to know how does the area look like. then you can just draw these projections. Okay, fine. I think these are parallel. So, see here again, you know that this area looks something like this. Okay. So, let us suppose this is your area A again. So, now see carefully, if this is your area and let us take the same small elemental area dA at this case, at which the pressure is P times of A. So, let us take the pressure is P in this instant along this. So, if this is pressure P, which you can write here pressure P, then let us suppose the centroid is somewhere here. Okay, we have seen already previously. Look, let us suppose the centroid is somewhere here. See, now if the centroid is somewhere here, then definitely we came to the conclusion that if this is your centroid, then in that case this will be your H bar. Yes. So, this will be your H bar, correct. So, this will be your see carefully, this will be your H bar. You can draw the diagram along with me. So, I am drawing so that even you will get the best idea out of this. Okay. So, if this is H bar, now if this is H bar, look carefully, then if you want to replace the complete force, normally you know we have the pressure distribution something like this, correct. So, basically we know, let us suppose the pressure distribution is you know something like this, for example. Okay. So, let us suppose the pressure distribution is something like this. Okay. So, I think you can find there is slight increase in this, correct. So, slight increase in this pressure. So, let us suppose then if this is your pressure which is varying in this direction, fine. So, see here, if this is your pressure, then we came to the conclusion that this complete pressure can be replaced with a single force F, correct. This is what we came to the conclusion from our previous discussion. So, we can replace this complete force with F. Now, if this is your F, that means you can take this projection again. So, if you take this projection again, your complete pressure is acting at some point here, correct. So, your complete pressure is acting at some point on this plate which is here. So, this is the point where your complete pressure is supposed to be acting. So, let us call this point as Cp, and this Cp at which this complete pressure force is acting on this plate, this Cp is called center of pressure. Center of pressure. Okay. And what is the center of pressure? The point at which the whole pressure force is supposed to be concentrated. So, if you are calling this as Cp, then this Cp is called center of pressure, and this is the point center of pressure. It is the point at which the total pressure force is supposed to be concentrated. Okay. So, is supposed to be concentrated. Okay. So, this is the total, this is the point at which the total pressure force is supposed to be concentrated. Now, see carefully, if this is the location at which your total force is acting, then if you take a balance about this moment, about this hinge O, the effect or the moment produced by this complete pressure force on this plate about this point O should be equal to the moment produced by this F about this point O on this plate, correct. So, for that what we can do, look here, what is the moment applied by this force? Let us suppose at this small elemental area, if the pressure is P, then if you call this distance as y, let us suppose if you are calling this distance, let us suppose if you are calling this distance as y. Okay. So, let us suppose if you are calling this distance as y. Okay. Now, what is the moment of this pressure force about this point O? Look, we can write this as small moment is nothing but P into dA. This is the force which is acting on this elemental area, and the moment of this pressure force about this O is nothing but this given by this length, which is y, correct? And if you want the total moment of this pressure force, we need to integrate this over the complete area, P dA into y, correct? So, can you all understand the total moment of this pressure force on this complete area is given by double integral over the area A, P into dA into y? Can you all understand this? Can you all understand that if P is the pressure at this infinitesimally small area dA, then definitely this P into dA is nothing but the pressure force which is acting on dA, and this pressure force into this y is nothing but the moment of this pressure force, elemental pressure force about this axis OX, yes or no? So, can you all understand this? Can you all understand this? If you can understand this, then we will go ahead for the next part. Can you all understand this first of all? Can you all understand this? So, please do type in the chat box. Can you all understand this? Let us suppose if I am telling you the small elemental pressure force which is acting on this elemental area dA is P into dA, then this P into dA into this y is nothing but the moment of this pressure force which is acting here, correct? Yes, we are using double integral because this area dA is a elemental area, okay? So, definitely we need to go for double integral, okay? So, that is equal to, now this total moment should be equal to the moment produced by this force, total force, which is capital F about this OX, correct? So, let us suppose this distance is, this is the point of action of this complete force. So, let us suppose this distance is y star, okay? So, let us suppose this distance is y star at which this is acting, y star, and obviously let us suppose this distance which is here is, let us suppose this is y bar, okay? So, y bar, let us suppose these are the three distances from this free surface. If this is the case, then the moment of this total force F about this hinge is given by F into y bar. Can you all understand this equation? Can you all understand this equation? If you can understand this equation, that is pretty much good, because the total moment of this, the total moment caused by this pressure force on this total area A is equal to, should be equal to the moment caused by this unit, a single force F about this point O. So, this is the equation that is with us. So, if you are clear till this point, then we will go for the derivations and all, okay? Because my main idea is to show you what is this y bar, or in general if you could y star basically. So, in general if you could, if you could try to identify this, this will be our H star as well, correct? So, this will be your, you can see this is your H star, see carefully, this is your H star, correct? This is your H star, okay? So, now see carefully, if this is the case and this is y star is what we have made. So, definitely this will be y star, correct? Why? Because it is y star, this F is supposed to be acting at a distance of y star from this, see this distance is y star and this F is acting at this location. So, the moment of this total force F about this axis OX is this F into this complete length which is y star, okay? So, this is what we have, clear? So, now let us try to complete the derivation now, but before going for that, let me shorten the screen a bit so that you all could see the things clearly, okay? Fine. If this is the case, then integral over A, this P is nothing but again the elemental pressure at this location which is at a height of y from this space is rho g into y sin theta into dA into y. This is what you have, correct? So, this will be equal to your F, total force that is acting on this plate. We have calculated that rho g A H bar, where H bar has its own meaning, into y star, correct? This is the thing that we have. Now, you can cancel one thing, this density and this acceleration due to gravity is constant on both sides. So, we will cancel this density and of course, acceleration due to gravity. So, if you cancel this, we have sin theta, if you take out a bit, sin theta into double integral over the area A, complete area A, y into y, it will give you y square dA, and this will be equal to H star into y, H bar into y star. This is what we have. Now, integration of y square dA is nothing but moment of inertia of this plate about this OX, yes or no, correct? Can you tell that double integral of this area A y square dA. This is nothing but moment of inertia of area A about the axis OX. Correct? Yes or no? Can you all understand this? Can you all understand that if I write sin theta into double integral of this area A y square dA, this double integral of A y square dA is nothing but we are measuring y from this OX axis. So definitely this double integral of A y square dA is nothing but moment of inertia of this complete plane about this OX axis. Correct? So can you all understand this part? If you can understand this, we will go for the next part. Clear? Are you all clear till this point? Are you all clear till this point that this double integral of area A y square dA, this will be equal to the moment of inertia of this complete area about this OX axis, because we have seen previously, look, we have seen double integral of x square dA means if this distance is x, then the double integral of this x square dA is nothing but moment of inertia of this complete area about this OY axis. Similarly, now since these are the distances, this y is the distance which is measured about this OX, so this is nothing but the moment of inertia about this OX. Now let us write this equation once again that we have sin theta into moment of inertia about the axis IOX. This will be equal to h bar into y star. Correct? H bar into y star. This is what we have. Now see carefully. Normally this distance of y star, or y bar changes depending upon the inclination of the plate. So if you define some axis, look, if you define some axis, define some axis such that, let us suppose this axis which we are drawing here, if this axis is okay, so fine, let us suppose this axis, or let me draw a bit neatly so you can understand this. So see here, let us suppose if I take an axis which is parallel to this OX but passing through the centroid of this plane lamina, and if I name this as XX for example, okay, this axis is parallel to this OX and also passing through the centroid of this area. Okay, so if this is the case, if this is XX, then can I write this IOX moment of inertia of this plane lamina about this OX axis is equal to moment of inertia of this axis which is passing through the centroid, which means IXX plus this total area, if I assume this as capital A, which we are doing so far. So A into, look, what is the distance between these two axes? You can clearly see the distance between this OX and this centroid is nothing but this y bar. So definitely we can write A into y bar square. Can I write this equation? Will you all agree with me if I say that this moment of inertia of this complete plate about this OX is equal to moment of inertia of this complete plate about this centroidal axis, which is also parallel to this, plus area into the square of the distance between them because of this parallel axis theorem. See, parallel axis theorem told us this moment of inertia about this axis OY is equal to moment of inertia about this axis which is passing to the centroid and also parallel to this, plus area into the square of the distance between these two axes. This is what we have seen. Correct? So similarly, if this is the case, can I write this moment of inertia about this OX is equal to moment of inertia about this axis which is passing through the centroid and parallel to OX plus area into this distance square, y bar square. So please tell me, did you all understand this part? So if you can understand this part, this is the key point for identifying what is the value of y star. Clear? So are you all clear till this point? If you are clear till this point, then we will go for the next part. Are you all clear? Can you all understand how this moment of inertia about this OX means this is OX, so moment of inertia about this OX is equal to moment of inertia about this axis plus area into square of this y bar square. Correct? If you can understand this, look, then I can write this, let us write this as y bar square directly, y bar square. So now, which means I can write this IOX as, which is here, okay, IXX plus AY square. So let us replace this here. So see carefully, sin theta into Ixx, which is the moment of inertia of this plane, which is parallel to this OX, plus area into y bar square is equal to h bar into y star. Okay. So now, you know, depending on the inclination of the plate, this y bar changes, but the depth h is dependent on this theta. And so now let us convert everything in terms of h. If you convert everything in terms of h, sin theta into Ixx plus a into, look, can I write y bar as h bar by sin theta? Can I write y bar as h bar by sin theta? Look, because this is y bar and this is h bar, and here your angle is, let us suppose if this is y bar and here your angle is theta. So can I write from this triangle sin theta is equal to h bar divided by y bar, or similarly h by y at any location. At any location, can I write this h by y as sin theta? So if you can write this, a into this y bar can be written as h bar divided by sin theta. So h bar square divided by sin square theta. This is what we can write always, and is equal to h bar into, now this y bar or y star, which is here, which we are denoting with this, you know, length. Y star means basically the location at which this total pressure is supported to be concentrated, is supposed to be concentrated. This y bar is equivalent to h bar, this you know, h star. Basically this y star which is here is equivalent to projected equal to h star. So now we can write this y bar as, or y star as h star divided by sin theta. Correct? You can write this. So now if you take LCM a bit, sin theta into Ixx sin square theta plus a h bar square divided by sin square theta is equal to h bar into h star upon sin theta. Correct? So similarly here, this is OG AH bar, there is one more A here which we left, I am sorry for this. So see here, there is this A which we need to write here, so there is one A here. So similarly there will be one A coming at every location here, into A, and of course here into A. This is what we will get. So now if you take LCM, this sin theta cancels this square, and of course one sin theta which is here gets cancelled because of this sin theta. So now if you divide this complete expression with A times of h bar, you will get h star is equal to, look, if you divide this complete expression with a h bar, we will get one h bar remaining here. So h bar plus, look, Ixx sin square theta, Ixx sin square theta divided by a times of h bar. Correct? This is the expression that you will finally get here. Yes. So center of pressure is at a depth of this much from the free surface. So are you all clear till this point? How did we get this? Just if you divide this complete equation with a times of h bar, for this Ixx sin square theta, there will be one a h bar in the denominator which you are seeing here, and this term if you divide with a h bar, a gets cancelled and one h bar gets cancelled. So you will have this h bar, and this side you will be left with only h star. So can you all understand this h star is equal to h bar plus Ixx sin square theta by a h bar, where this Ixx is nothing but the moment of inertia of this plane area about the axis which is passing through the centroid. Can you all understand this? Ixx is the moment of inertia of this complete plane area about this centroidal axis xx. So if that's the case, then if you know Ixx, definitely once you know what is the plane, then you can calculate your Ixx from the standard values of your basically your engineering mechanics classes. Then theta is given, means it's given by what angle this plate is inclined to that free surface. So again this h bar is also known to us. Area is known. Once the plate is given, you can find what is area, and centroid you can easily find what is the depth of centroid, basically because this y bar you know, because if this is the plane area, you know what is this y bar. So depending on this theta, you can calculate what is this h bar also simultaneously, which means the complete total force acting, total pressure force acting on the plane surface, is equal to rho g a into h bar, and the depth of center of pressure, from free surface. Center of pressure from free surface. From free surface is given by, what is the value by which it is given by? This is given by H star is equal to H bar plus Ixx sin square theta divided by A times of H bar. Okay. So, this is what you have. Yes, H bar is the vertical distance of force acted upon. Yes, because I have clearly mentioned this H bar, this H star basically, this H star is nothing but this vertical distance of this location of this center of pressure from free surface. Similarly, H bar is the vertical location of the centroid. I have marked already, like in previous diagram as well. So, this is basically your centroid C, and this is your center of pressure, and you can see clearly that this basically this value H star is equal to H bar plus some positive value, because this value is completely positive, because moment of inertia is always positive, sin square theta, theta is positive, I mean theta is acute, so sin square theta is positive, area is positive, and H bar is also positive. So, definitely this H star will be more than this H bar as compared, and that is why I know this before. So, intentionally I have drawn this force below this H bar, correct. I have drawn this force at a location which is much below this H bar, clear. So, that is the reason why I have taken this force below this H bar, because I know that finally you are going to get H bar plus some positive value, clear. So, are you all clear till this point? If you are clear, then we will go for the next things. Okay. So, this is the case, and if you want to read all this diagram once again, I would like to show you. Look, so whenever there is some bulk of static fluid, so whenever there is some bulk of static fluid, then you can clearly understand that if this is your plate which is at some angle like this, and of course at some depth as well. So, let us suppose if okay, so let us suppose if you are drawing some more liquid at the bottom, and now let us suppose if your area is something like this. Okay, this is your area A, this is your area A, then your complete pressure force on this is equal to, let me summarize the result. So, your complete pressure force will act at this location which is a bit lower than this center of centroid basically. So, this F is equal to, if you call this as your F basically, so this F is equal to rho g times A into, where A is the area of this, into H bar. Okay, let us not put the into in between. So, this is H bar. Okay. So, where this is your centroid C and this is your center of pressure. Similarly, if you see, this is your centroid C and this is your center of pressure. Okay. These two will be actually on the same horizontal line. I will tell you why it happens. Okay. Maybe in tomorrow's class. So, is it possible that somehow center of pressure act above the center of gravity, means we can use this formula in this situation? No, it can't, because I will tell you what are the cases in this. Okay. So, see here, this is your H bar. So, see, this is your H bar, which is always measured from your free surface. Okay. So, if this is your H bar, and then this rho g A times of H bar, you know how to evaluate this. And if you want to identify what is this center of pressure location, then this axis x axis basically. So, this axis is, let us take the help of a straight line and let me draw. So, this axis is some axis like this. Okay. So, which is parallel to this reference axis, and of course, basically passing to the centroid. Okay. So, if this is the case, your x x is this axis, means you are going to consider the moment of inertia about this axis x x. Okay. So, I think by this time you got the idea of this complete two formulations. Okay. And let us suppose if I am calling this force as F, because I am replacing this with F always. So, if I call this force as F, then you can also see this value is equal to rho g A times of h bar. Okay. So, this is what we have. So, basically many times we need to identify what is the location at which the pressure is supposed to be acted, because for many of our calculations in engineering applications we need to identify what is the location at which this whole pressure can be, all whole pressure force can be replaced. Okay. So, this is the reason why we calculate this h star in general, because center of pressure is a very important concept in actual practice. Okay. So, we have these two formulas summarizations from this lecture, and also if you see, I would like to give you some conclusions at this point. Look, case 1, let us suppose if plate is horizontal or if plane is horizontal, if plane is horizontal means how is it horizontal? When your theta is 0, correct? If your theta is 0, look from this diagram, this is your theta. If your theta is 0, which means this plate will be actually parallel to the free surface of the fluid, correct? So, basically like in this case you can see, whenever your plate is at some angle, this is the analysis that we got. But now when your theta is 0, this plate gets horizontal, correct? So, when this plate gets horizontal, let us see what happens. When this plate is horizontal, look, let us suppose this is the case and your plane surface is horizontal. Okay. So, when your plane surface is horizontal, then in that case, I am sorry, I am trying to draw it vertical, I guess. Okay, fine. Now it is horizontal. Okay. So, if your this thing is horizontal, then you can always observe that if this is the axis at which your centroid and center of pressure are located, then you can see clearly this is the, okay, let me use a straight line for this purpose. So, let us suppose if I am using a straight line, okay, and here even, so you can see this height which is equal to h bar, and also this will be equal to h star. And why this happens? Because you can see in this formula, if you put theta is equal to 0, this term completely goes out, correct? Because sin 0 is 0 and sin square 0 is also 0. So, this term completely goes out. Pressure distribution is same, yes, on the horizontal surface plate as we have studied till here. Yes, of course, Rajnish, correct. So, if theta is 0, then this case will, this term will get eliminated, and this h star is equal to h bar, means the center of pressure and the centroid are at same height. And if you talk about pressure variation, how does the pressure variation look like in this case? You can see how does the pressure variation look like in this case. Basically, it is uniform, because we have studied that in a horizontal plane of a static fluid the pressure never varies. So, if this is the case, then we can easily identify that. Let us just quickly join these 2 points as well. Okay, fine. So, now let us see, this is your total pressure force which will be acting on this plate. Fine. If this is the total pressure force which is acting on this plate, then what is this pressure? Definitely this pressure force, this P will be equal to rho g times h bar, correct? Because when this plate is at a depth of h bar, and let us suppose if I am talking about gauge pressures with respect to atmospheric pressures, then this P will be equal to rho g h bar. So, what is the total force that will be acting? Total, or you may write, let us write total pressure force. Total pressure force from fluid statics means from the second module, whenever this plate is, or the axis of this plate is at an angle of, at a depth of h star from this free surface. Let us suppose if this is your free surface. So, when this is at a depth of h star from your h bar from your free surface, the pressure that is acting is uniform in any horizontal plane, and the value of that gauge pressure will be equal to rho g h bar, correct? So, this is rho g h bar into this area of the plate. We know force is nothing but pressure into area, and since pressure is constant in this case throughout, or same uniform in throughout. So, definitely this rho g h bar into A is the total pressure force. So, F is equal to rho g h bar into A. And next, again, what is this h star? Definitely this h star will be equal to h bar. Why? Because I h bar plus I g g or I x x, let us suppose if you are calling Ixx, this Ixx sin square theta by AH bar, this theta is 0, you can write this value is 0 when theta is 0. So, definitely your H star will be same at the same depth, which is equal to this H bar. Okay. So, this is what you can always write. In case of horizontal case, did you get the idea what we are going to do? Did you get the idea what we are doing? And definitely this complete pressure force is supposed to act at some this location, basically at this centroid, okay, as long as this plate is horizontal. So, okay, fine. So, this is your F, F, which is equal to rho g h bar into A. Fine. So, this is how we will get the value of this total pressure force which is acting on this plane whenever this theta is 0, okay, because in this formulation if you substitute theta is equal to 0, which just now we have seen. So, this theta is equal to 0 implies your H star is equal to H bar. Next, let us suppose the case when plate is vertical, case 2. Let us write this, case 2. When plate is vertical, when plate is vertical, okay. So, when plate is vertical means basically in a bulk expanse of fluid, if you having your plate to be vertical means something like this. Look here, if this is your free surface again, so let us suppose if this is your free surface, then let us suppose your this plane is at an angle of 90 degrees, means now it is vertical, okay, because you have seen this is the angle theta which we have defined here. So, if this is the angle theta, if theta is equal to 90, this plate which is initially at some inclination, it gets straightened, correct. So, basically this will stand vertical. So, now if this is standing vertical, definitely this is some location of this centroid which is C, and this is some location of your center of pressure, correct, Cp, which we have seen just now. And now if you see carefully, let us suppose if you are drawing the side view of this, for example, okay. So, let us suppose if you are trying to draw this, let me take a dotted line. So, let us suppose if you are taking the side view of this, fine. If this is your side view of this plane, okay, and definitely let us suppose this is the projection of your centroid even, okay. So, let us suppose this is the location of your centroid C. Now, if you define an axis Ixx which we are defining so far, so let us suppose if this is the axis which we are defining as your Xx, because this is the axis which we are defining as Xx so far. So, you can see if this axis is your Xx, then if you calculate this H bar and H star values, see how does the values occur, okay. So, let me write this, and this will be your H bar, okay. So, see here, basically this is the location of your center of pressure and this is the location of your centroid, okay. So, if this is the case, then this value is your H star, which is your center of pressure from vertical distance, and of course, this is your H bar, okay. So, when you have these two things, okay. So, see here. So, I hope things are clear, correct. So, force on this plate, basically what is this plate? Force on total pressure force, you can see total pressure force acting on the plate, total pressure force acting on the plate is equal to rho g A times H bar, where of course this area is again A, which we are generally denoting this area is A, and then what do we have? This center of pressure H star is equal to H bar plus Ixx, and in this case this sin square theta value will be 1 divided by A times of H bar, okay. So, once you give the cross section of this plate, for example circle, triangle or some other things, then you can easily write what is this Ixx about the axis parallel to this, I mean passing to this centroid basically, correct. So we can write this value. So which means one thing is very clear, this H star is very much lower than this H bar. Okay. Now one very important thing to observe is, if you keep on putting the plate down, means if there is some free surface, and let us suppose if you are pulling the plate down to some extent. Now if you are pulling the plate to much still extent, then definitely your H bar and H star will become almost equal, correct, because this moment of inertia values are generally small, and of course this H star, if you keep on increasing, and this area is also of some finite some considerable value. So definitely this for long depth, means if you keep on increasing the depth of this plate from the free surface, then this H star and H bar will become almost equal because of this H star in this denominator, and also some area, because generally area is a bit in case of gates and all, in actual practice this is in some meter square, and definitely if you multiply this H star with means basically this product upon this Ixx will give you some little value, and of course this H star will be almost equal to this H bar whenever your depth is so large. Okay, means the depth of immersion of this plate is so large. Okay, so are you all clear till this point? Are you all clear till this point? In both the cases, this is free surface. Okay, I am talking about free surface in this case even. Okay, so this is free surface. Clear? Rho g A times of H bar, and what is the dimension of this H bar from this top surface, because the plate is vertical, correct? So you can easily identify. Now let us take one special case before leaving, because we have some time, some 5 minutes of time. So let us talk about one more case. Case 3. When the free surface is subjected to some external pressure. When the free surface is subjected to some external pressure, So what is this some external pressure? Let us see carefully, because this is one case in which you get some questions in GATE exam as well many times. So that's the reason. See here. Let us suppose this is your free surface. Okay, let me not draw this much height because I want to do something. So see here. Let us suppose if this is your free surface. Now if this is your free surface, then let us suppose again you have some plane surface basically, some plane which is again inclined at some angle, or else let us keep it straight for the time being, no issue. So let us suppose this is the case, okay, because by this time you already know how to do with the inclined surface and all. So now let us suppose this pressure at this surface is P is equal to something, P naught. Okay, it's not P.ATM, but some other pressure because of some high compressed gas above this surface, or because of maybe some other fluid layer above this surface. Let us suppose this is not at atmospheric pressure, because the assumption that we took initially when we are deriving this total pressure force is basically only one side of the one surface or one face of the plane is subjected to some fluid, and the other face is left to atmosphere. But now in this case, let us suppose if the pressure at this free surface, of course, even though in this case even one side is subjected to fluid and one other side is left to atmosphere, but let us suppose if this pressure at this layer is not equal to P naught, I mean not equal to atmospheric pressure, then how to deal with the case? Look here, can we write P naught is equal to rho of this fluid into G into some value H? Yes or no? Can I write whatever is the pressure here, that pressure will be equivalent to some pressure due to some some height of this same fluid column, correct? Can I write this? If there is some pressure at this free surface P naught, then can I get one value of H such that this P naught, which is the pressure at this free surface, will be equal to density of this fluid into acceleration due to gravity into H? Yes or no? Can I get this head? Basically this head of this fluid is nothing but P naught by rho g. Can I get this? Because I know what is the density of the fluid in which I am inserting my plate, and of course I know what is the value of acceleration due to gravity, and if I know what is the surface pressure P naught, then can I get some height of the fluid at which this pressure because of this fluid column will be same as P naught? Yes or no? So please do type in the chat box. can I get some value of H such that this H is equal to P naught by OG? So please tell me. Yes. Now what we'll do in general practice, above this free surface we'll increase the level of fluid. Okay. So basically we'll increase this level of fluid. Look, we'll increase this level of fluid. And maybe here. Okay. So let us suppose this length to which you are increasing this fluid is H. H, okay, and this H is actually calculated from this value. Okay. So if this value is H, then this H is calculated from this value. Now if there is fluid column of height H, definitely here the pressure at this point will be, at every point in this horizontal plane will be P naught, no issue, because P naught is equal to O times of GH. Yes, assuming extra fluid about this, correct. We are making this assumption such that there is some extra column of this same fluid above this free surface such that this H value will be equal to P naught by OG. Means my main intention is to show you, let us add a fluid column of height H which could produce the same effect of a pressure P naught on this particular surface. Is that clear to all of you? Is that clear? Is my statements clear? Look, I am telling, I am adding an excess layer of fluid such that the pressure at this layer P naught, and at this layer at a depth H from this free surface will be again P naught. Correct? Can you all understand this point? If you can understand this point, then now here again the pressure is P atmosphere. Correct? Again its local pressure. So this acts as a free surface. So if the centroid is at this location, let us suppose if the centroid is at this location, see, this time we measure H bar. This time we measure H bar from this location. Okay. So if you measure H bar from this location, then what happens? Undoubtedly your previous all your derivations gets valid again, because here again the pressure is atmospheric pressure and one side you are leaving to air. So definitely this is the case. So H bar will be something like this. Okay. Depth of this center of pressure from this, depth of this centroid from this free surface. Clear? Depth of this centroid from this free surface, because the only thing is your all derivations which you have done till now are valid only when the free surface pressure is, atmospheric pressure. But now if you have some excess pressure or maybe some lower, some excess pressure in general, if there is some lower pressure, we will reduce the layer of this fluid in general. Okay. So but in general, if some top layer of the fluid is subjected to some external pressure, then what you will do? Definitely you will increase the some excess column of fluid which is equal to P naught by OG. So now this is again acts as a free surface, and again you can measure your H bar, means basically the depth of this centroid from this free surface, and all your derivations, all your total pressure force P, total pressure force P is equal to rho G A H bar. Correct? This is the same case, and again using this as H bar, you can also calculate the location of center of pressure, H bar plus Ixx sin square theta by, of course in this case it is vertical, so sin square theta is 1 anyhow, so Ixx divided by A into H bar square. Is that clear to all of you? Is that clear to all of you? Are you all clear? Whenever the surface is subjected to some external pressure, how to deal with the case? Yes, is that clear to all of you? Yes. So basically this is hydrostatic forces on free surfaces, and there is one small topic which is left over, but our time is out for today. So basically I have told you about this variations of H. The only one good point that I want to tell you again at this moment is, look, basically this H bar will be definitely lower than, this H star depth will be definitely more than this H bar. This is what we have seen, but my only intention is to tell you that let me take this line for the time being. So my only intention is to tell you that these two fellows, center of mass, this centroid and this center of pressure, both lie on the same line. This is the only thing that I want to tell you, and that I will tell you in tomorrow's class. Maybe it may take some 5 minutes, only we deal with some product of inertia because it's already time for today. Okay. So maybe we deal with some product of inertias, and I will show you that this center of basically center of gravity of this plane and center of pressure of this plane both lie on the same vertical same line basically. Okay. They both lie on the same line, means basically there is no difference between these two. Clear? This is the only thing that is left over. I will maybe I will cover in next lecture for 5 minutes, then we move on to the hydrostatic forces on curved surfaces. So are you all clear with today's lecture? Let us quickly revise the things that we have learned today. So basically we have seen what is the idea of, okay, we have seen what is the idea of centroids. Then once we have seen what is the idea of centroids here, then we moved on to what is the finding total pressure force that's acting on a plane surface. Then once we have find what is the total pressure force that's acting on a plane surface, then we moved on to how the pressure variation look like, and of course this complete pressure forces can be replaced with a single force system or single force, which is F is equal to ρg times area of this plate into h bar, where h bar is the depth of this centroid from this free surface, correct. Then we have seen some definitions of moment of inertia and some recapitulation of all these things. So where can I find the notes of these topics? I am on daily basis I am uploading these notes on Telegram channels of Engineers Hub. Just a moment, Sandeep Chandu, I'll show you the place where to get these notes. Okay, so there is something called the parallel axis theorem, where you can apply this parallel axis theorem and you can calculate moment of inertia about any parallel axis. So once we have done with this, we have dealt with this diagram, which is, of course, it looks like there are many lines involved in this, but of course this is a very simple diagram. There is only three constructions, this y, y star and y bar, and similar three projections for h, h star and h bar. Okay, so that's the only thing. So just by applying a bit of moment balance, we got the formula for center of pressure, which is h star is equal to h bar plus I xx sin square theta by a times of h bar. This is what we have got. Sir, last class notes, I didn't upload that. I think I have done that. Last class notes in sense you mean problem solving session, correct? Okay, I'll upload that, no issue. Okay, I'll definitely upload the problem solving session notes in this in Telegram channels, and also if possible I very soon will have a provision to upload this PDF in the app as well, okay, for the problem solving session, so you can download that. So look here, if this is the case, then we have summarized the result basically. So if this centroid is lying at an angle something like this, then here one thing I would like to draw here at this moment. So basically this angle is your theta, correct? This angle is your theta, because when you are putting theta you should know what is theta, so that's the only thing. So see here, if this is the case, then we have three different cases. When plate is horizontal, so basically when plate is horizontal, we have seen what is the total pressure force that's acting on the plate. Basically it's ρg h bar into a, and in this case h bar and h star both will be having same depth because of this sin square theta becoming 0. That's what even I have written there. So in second case, when plate is vertical, this is the formula, because theta value is 90 and sin square theta value is 1. Okay, yeah, inclined tube manometer I'll upload, no issue. Look here. So in the third case, whenever this surface is subjected to some external pressure, we add an xx bulk of fluid of column, which is equal to P naught by ρg. So once we have this column depth, then we'll measure this h bar from this surface, which could fit our analysis. Very good. Okay, so these are the things that we have covered so far, and in tomorrow's class the only thing that's left about this hydrostatic forces on free surface and on plane surfaces is to show you that this both C and Cp lie on the same straight line. Actually that takes some 5 minutes, because we need to deal with some product of inertia, and that's the reason. Okay, I'll take in the next class maybe for 5 minutes, then we move on to the concept of hydrostatic forces on this curved surfaces. Okay, so this is one very important lecture, because in GATE many times questions definitely come from this curved surfaces as well and plane surfaces. Okay, in GATE almost every year there is one question in mechanical or civil and in all other branches definitely. So please don't miss this session, okay, because this is a very small module and it's only of 2 lectures. Okay, one on plane surfaces which we have done today, and one on curved surfaces which we are going to deal tomorrow, and on Saturday we are going to have problem practice session on all this problems of this plane and curved surfaces. Okay, it's a bit heavy today, correct? Even because yesterday it's a bit short, so I need to compensate, right? And what about India's match? I think our bowlers are doing good, correct? Anyhow, after live I am going to have a glance at it. So fine, see here, as I told you, we have started this offline batch. So second batch is going on as of now. We have started this on the last Monday and it's going successfully, and the next batch and the last batch is going to be started from 29th of March. Okay, so please try to join as soon as possible if you want to have some guidance from the best team at Andhra Pradesh. Okay, so definitely the timings of the batch are from 2 p.m. to 7 p.m. and also the batch duration generally extends for 5 to 6 months, so that we'll be having enough time so that you can cover all the concepts and all the topics in a very thorough manner. Okay, and also apart from all these things, we will also get guidance from Negi sir and his team which is at Engineers Hub. That's for you. And of course, these are the contacts, and few of you are asking me to upload the notes and where can I get the notes and all. So basically these are the two places where you can get the notes. For example, this is Engineers Hub mechanical page, mechanical Telegram channel, and of course this is for Engineers Hub ECA, CSE and others, means basically civil engineering, chemical, all others can get the notes from this location. So these are the two places where basically you can get the notes on daily basis, where I am also posting the notes on daily basis. Okay, and this is the official YouTube channel of Engineers Hub. So from official YouTube channel of Engineers Hub, we are going to get a lot of useful information, because there is some playlists which are very helpful for you. There is one complete mathematics course which is done for free by me. You can always have a glance at that, and even we have free basic thermodynamics course completely free. Okay, you can have that revision to this basic thermodynamics course, and you can get some knowledge as well. And all the official updates of this Engineers Hub you can get in the Twitter handle, Facebook page, and also in the LinkedIn profiles, and also in the official website of Engineers Hub, engineers-hub.com. So if you type engineers-hub and .com, you will definitely get all the recent updates and all the important content of Engineers Hub at these locations. Okay, so you can get all the updates from this location. And if you are on this channel for the first time, please do hit the subscribe button and also click the bell notification, so that whenever we are going to start any class or any event, you will get notified. Okay, and as long as as far as gate results are concerned, we are expecting that it may get released tomorrow. So anyhow, I wish you all a very good luck at the end. Okay, so thank you all. We'll meet tomorrow sharp at 9:30 p.m. and we'll see this some 5 minutes topic on this plane surfaces, and also something on this curved surfaces. Okay, so thank you all. Have a nice time. Good night. We'll meet tomorrow sharp at 9:30 p.m. Thank you.